Hello, silicon pioneers. Welcome to SemiSlides, where semiconductor know-how meets sharp visuals and clear explanations. In dry etching, the goal is to transfer the lithography pattern and photoresist into the silicon wafer with fidelity. As devices scale down, vertical profiles, precise CD control, and tight overlay become non-negotiable. Meeting those demands begins with understanding what the plasma is doing on the wafer's surface. This series explores the fundamentals of plasma etching used across the industry. It is organized into 4 parts. Part 1 explains why vertical etching is required, and how a plasma enables it. We build intuition for isotropic and anisotropic behavior, and we introduce the 4 basic dry etching mechanisms. Part 2 moves inside the discharge and down to the surface. We clarify the roles of electrons, ions, and radicals. Electron impact drives dissociation for radical generation and ionization for ion generation, which together power plasma etching. Excitation produces light emission, and that signal is the basis for optical endpoint detection. Part 3 focuses on the outputs you must analyze during and after etching. We cover process responses such as etch rate, selectivity, and etch amount. We also cover pattern transfer metrics such as repeatability, uniformity, etch target, loading effects, and plasma-induced damage. Part 4 introduces the inputs that control those outputs. We connect wafer conditions, etch targets, tool settings, and recipes to chamber settings, plasma settings, feed gases, and gas flows. Our approach keeps math light and concepts front and center. Step by step, we move from first principles to practical techniques. By the end, you will have both physical intuition and working insight for plasma etching and device fabrication. Let us begin. Please note that my content is exclusively for YouTube, and any uploads found elsewhere are unauthorized. Each video is meticulously crafted, akin to the precision of silicon wafer fabrication, involving a month-long process with late nights and ample coffee. Discovering my content on platforms other than YouTube is disheartening and impacts my motivation. Supporting the idea of open knowledge sharing should not be mistaken for allowing the redistribution of my content elsewhere. Your understanding in upholding creators' rights is appreciated. Let me begin by explaining where plasma etching fits in the semiconductor fab process cycle and why it is essential. Semiconductor manufacturing divides into wafer-level fabrication in the fab and package-level assembly and test after the fab. Our focus is the fab flow, where a bare silicon wafer becomes an integrated circuit by building transistor-level structures and then connecting them with multi-layer metal wiring. The fab flow has 3 major sections. Front end of line, FEOL, creates the transistors. Middle of line, MOL, links the transistors to the first metal level through local contacts and vias. Back end of line, BEOL, builds the stacked interconnect that carries signals and power across the chip. In back end of line, the factory repeats 2 pattern types again and again, metal patterns and via patterns, and these repetitions create the global and local wiring network. In dual damascene back end of line, the etch first forms vias and trenches in the low-K dielectric. Barriers and copper later fill these shapes, and polishing removes the overburden to reveal flat metal lines. This combination of precise pattern transfer and planarization is repeated layer by layer until the full interconnect stack is built. Each wiring or via level follows a common process cycle: deposition, photoresist coating, exposure, developing, etching, copper electroplating, chemical mechanical polishing, and cleaning. Photolithography writes the image into the photoresist with precise coating, exposure, and development. Plasma etching then performs pattern transfer. It removes the exposed parts of the target film while the mask protects the covered parts, so the resist image turns into trenches and vias with accurate width and depth. After the openings are created, copper fills the features and polishing and cleaning finish the level so the surface is ready for the next cycle. Although a single chip requires well over 1,000 steps across several months, the local logic at each layer stays simple: make films by deposition, write the image by lithography, transfer the image by plasma etching, then build and planarize the structure for the next level. This is how plasma etching anchors the process cycle inside the semiconductor fab. The mission of plasma etching is constant across all these cycles: Transfer the resist image into the underlying film with accuracy, selectivity, and profile control. Accuracy means the critical dimension and overlay remain within tight limits set by the design rules. Selectivity means the etch removes the target material while preserving the mask and the etch stop films. Profile control means vertical sidewalls, clean bottoms, smooth surfaces, and the intended depth, which together secure electrical performance and reliability. The objective of plasma etching process is precise pattern transfer with tight control of critical dimensions and sidewall profile. The photoresist route is straightforward. Deposit the target film, coat and bake the resist, expose and develop to form the relief image, etch the target film through the openings, then remove the resist and clean the surface. This route works well when the resist is thick enough and when the etch chemistry has good selectivity to the resist. The hard mask route is chosen when the resist alone cannot survive the etch. This happens with deep features, long overetch requirements, high aspect ratio structures, or when the target chemistry attacks the resist strongly. Deep UV and EUV lithography often uses a very thin resist, so a hard mask is frequently required to protect the pattern during transfer. Common hard mask materials include amorphous carbon, silicon dioxide, silicon nitride, silicon oxynitride, titanium nitride, and metal oxides. Material selection follows the selectivity needed against the target film in the plant chemistry. Fluorocarbon plasmas show high selectivity to amorphous carbon, which makes it a strong choice for oxide etches in back end of line. Hydrogen bromide and chlorine-based plasmas show high selectivity to silicon oxide and silicon nitride, which supports polysilicon and metal gate etches in front end of line. Hard mask deposition uses plasma-enhanced chemical vapor deposition, low-pressure chemical vapor deposition, physical vapor deposition, or atomic layer deposition depending on stress, conformality, and thickness targets. Thickness is set by the selectivity budget and the overetch margin. A typical hard mask is 1/3 to 1/2 of the resist thickness that would otherwise be needed. Thicker hard masks improve durability, yet they also increase etch time during the open step and can add reflectivity issues for lithography, so balance is important. The patterning sequence is as follows. Write the image and resist on top of the hard mask by lithography. Open the hard mask with a short selective etch that minimizes roughness and controls the top corner. Apply a trim if needed to tune the critical dimension by a few nanometers and to compensate for optical bias from lithography. Strip the resist and clean the surface to remove native oxide or polymer, for example a brief hydrofluoric acid clean before an oxide transfer or a dilute sulfuric peroxide clean before a metal transfer. Use the hard mask to drive the main target etch with stable sidewalls and long overetch capability. Process control relies on accurate endpoint detection and balanced plasma conditions. Optical emission and laser interferometry track the moment when the hard mask opens and when the etch lands on the stop layer. Profile control uses the balance between ion energy and sidewall polymer formation to hold vertical walls while keeping the bottom clean. A hard mask reduces line edge roughness transfer from the resist and reduces profile swing during long etches. Use the photoresist only route for shallow or low selectivity transfers where the resist has enough thickness and durability. Use the hard mask route when you need long overetch time, when the chemistry is aggressive to resist, when features have high aspect ratios, or when the imaging resist must be very thin. Both routes meet the same goal: clean and accurate pattern transfer by plasma etching, followed by clean removal of temporary materials to secure yield and reliability. This slide is about directionality, the reason plasma etching is used for advanced patterns. We will move from the big picture to specific outcomes and contrast isotropic and anisotropic behavior as we go. Isotropic etching removes material at nearly the same rate in every direction. The mask edge undercuts, corners round, and the opening widens as the etch goes down, so control of the printed width is weak. Anisotropic etching removes mainly downward. Sidewalls remain straight, the printed width is preserved, and the final depth and angle can be held tightly. What drives each behavior is the mix of chemistry and direction. Isotropic behavior appears when neutral radicals dominate at higher pressure with little or no wafer bias. Anisotropic behavior appears at lower pressure with a narrow ion angle distribution and a controlled bias, and a thin passivation film protects the sidewall while ions clear the bottom. This difference shows up as process control. With isotropic etching, lateral attack is built in, so control of critical dimension and sidewall angle is limited. With anisotropic etching, ion energy is steered normal to the wafer and passivation sets the wall, so width, depth, and angle can be tuned precisely. The limit on minimum feature size follows from that control. Near 20 nanometers, even a small undercut breaks the rules, so isotropic etching is not suitable for fine pattern transfer. Anisotropic recipes can transfer below 20 nanometers and support very high aspect ratio shapes when bias and passivation are balanced. Speed is different as well. Isotropic processes are often fast because reactions are chemistry limited and not constrained by direction. Anisotropic processes run at moderate speed because the recipe trades rate for verticality and bottom cleanliness. Mask survival follows the same logic. Isotropic routes usually show high selectivity to common masks, so the mask lasts while the target film is removed. Anisotropic routes deliver lower selectivity to photoresist under bias, so a hard mask is used to survive long ion bombardment and long overetch while still landing cleanly on stop layers. Throughput and cost are a consequence. Isotropic steps give high throughput and lower cost for cleans and recess work. Anisotropic steps take longer and cost more, yet they are essential when pattern fidelity and landing accuracy matter. Each approach has a natural home. Use isotropic etching for surface clean, resist descum, recess etch, sacrificial release, and intentional corner rounding or crystallographic shaping. Use anisotropic plasma etching for fine pattern transfer, contacts, vias, trenches, spacers, and deep memory channel holes where aspect ratio can approach 60 with a durable hard mask. That is directionality in practice, lateral removal for speed and selectivity when shape is not critical, and vertical removal for the precise features that make the chip work. From now on, let me introduce the beginning of plasma etching and show how early reactor designs moved from resist etching to true pattern transfer. The story starts in the late 1960s when Stephen Irving at Signetix demonstrated that oxygen plasma could strip photoresist cleanly and repeatably. Industry commonly used a tracer lab-style system that placed the work inside a quartz vessel while an external coil sustained an electrodeless discharge around the tube. The basic idea had roots in 19th-century induction experiments reported by Thomson, and it later converged to radio frequency operation that the industry standardized near 13.56 MHz. By 1971, Irving reported silicon etching in carbon tetrafluoride and documented gas plasma vapor etching methods. The push toward plasma came from a need to reduce wet chemicals and from the desire to reach hard films like silicon nitride and thermally grown oxide with cleaner profiles and better line edge preservation than wet etching could offer. The left figure shows the barrel reactor that defined those early years. Wafers sat on a quartz boat inside a quartz tube while process gas flowed through the chamber and an external coil drove the discharge. The plasma filled a large volume and the wafers were far from the sheaths, so ions were largely thermalized and neutral radicals dominated the reactions, which made the behavior essentially isotropic. Uniformity was limited by gas depletion along the tube and by shadowing around the boat rails and wafer edges, and wafer temperature floated with plasma heating and radiation because there was little direct thermal control. The configuration was excellent for oxygen resist stripping and gentle cleans, and it reduced metal contamination by keeping electrodes out of the plasma, but it struggled with precise pattern transfer. The right figure shows the radial flow reactor, often called the Reinberg reactor, which made plasma etching practical for production. Gas entered near the center, then spread radially across the wafer plane while the vacuum port drew it out through the center, and the facing powered and grounded electrodes created a controlled plasma gap above the wafers. This pancake geometry shortened residence time, improved distribution, and allowed stable wafer heating and cooling, which tightened within wafer uniformity. Interestingly, engineers had explored this layout for plasma-assisted deposition of protective films and then recognized that with bias control it could etch patterns with much better fidelity. These steps set up the transition to parallel plate reactive ion etching, where a self-bias at the wafer drives directional ions and sidewall passivation can be tuned for vertical profiles. From the barrel asher to the radial flow tool and onto parallel plate architectures, the hardware evolution turned plasma from a cleaner into a precise pattern transfer engine. Continuing on, This slide explains how plasma etching moved into real device fabrication during the early era of large-scale integration and why the shift happened. Look at the left graph. Design rules shrink as memory density rises, from early kilobit parts to 16 kilobit and 64 kilobit generations. Those milestones mark the moment when liquid etching began to give way to plasma-based steps across the fab. In the production flow of that time, the silicon nitride barrier used for Loco's isolation was removed by hot phosphoric acid and related mixtures after a short hydrofluoric pre-clean. These liquids often showed an incubation delay before etching, they attacked common photoresists, and they produced isotropic profiles that undercut the mask and loosened critical dimension control. Plasma solved those two pain points: resist damage and timing control. At the 5 micrometer class around the 16 kilobit DRAM node, factories adopted oxygen plasma ashing and isotropic plasma etching with carbon tetrafluoride in barrel-style tools, which made resist strip cleaner and made timing more repeatable than the liquid route. Texas Instruments soon showed that an entire device module could be processed without liquids, reporting a fully dry-etched device in 1975 and proving that plasma was more than a niche step. Even then, the etched shape was still isotropic because the chemistry dominated and lateral attack remained. Scaling pushed harder on shape control. Design rules tightened from about 5 micrometers to about 3 micrometers, and wafer size moved from 3 inches to 4 inches, which amplified uniformity and critical dimension requirements across the plate. The breakthrough for profile control was reactive ion etching. For the 64 kilobit generation, contact holes and other features were etched with carbon tetrafluoride mixed with oxygen under bias in parallel plate reactors. Directional ions cleared the bottom while a thin passivation held the sidewall. Printed width was preserved and the etch landed cleanly on the stop layer. This single change cut critical dimension loss and stabilized the overetch window, which made contacts and fine openings practical at that node. As oxygen ashing and plasma etching took hold, the whole line changed. Dry steps replaced many wet steps, the count of process operations dropped, uniformity improved, and yield rose as particle and corrosion risks fell. Applications spread quickly from isolation and gate work to contact windows and interconnect etches, and plasma became the default engine for pattern transfer. By the mid-1980s, reactive ion etching had replaced most pattern-defining wet chemistry in very large-scale integration, while liquids remained for targeted cleans and stripping. That is how plasma etching entered device fabrication, first as a cleaner and then as the method that delivered directionality and repeatability for scaled features. There are 4 basic low-pressure plasma processes commonly used to remove material from surfaces: sputtering, pure chemical etching, ion energy-driven etching, and ion inhibitor etching. This slide defines sputter etching, and highlights its 2 defining limitations. Sputter etching is a physical removal process, where ions, accelerated by the sheath, strike the surface and transfer momentum to eject atoms through a knock-on cascade. The bombardment is directional, so features follow the arrival direction, and the profile is strongly anisotropic. First key point is low mask selectivity, and the cause is the energy scale mismatch. Sputtering is an unselective process since the sputtering yield at a given ion energy depends on the surface binding energy and weakly on the masses of the targets and projectiles. Greater than the bonds between the target atoms must be broken, and the surface potential must eventually be overcome for the etching. Because the ion energy is far above bonding scales, chemistry cannot meaningfully protect one solid over another. Typical wafer-level ion energies are in the tens to a few hundred electron volts, while surface binding energies are only a few electron volts. Removal is governed by momentum transfer and binary collision kinematics, rather than by differences in bond strength. Therefore, the sputter yield follows projectile mass and scattering geometry more than material chemistry. As a rule of thumb, at tens to a few hundred electron volts, the yield ratio between silicon and silicon dioxide is often only about 1 to 3, whereas chemically driven etching can reach 10 to 100. Hence, the sputtering rates of different materials are roughly the same. Hence, pure sputter removal keeps mask selectivity low. Second key point is top corner rounding, and the cause is angle-dependent contact volume. Sputter yield increases strongly with oblique incidence, because an angled trajectory engages a longer near-surface path and a larger collision volume. The local maximum commonly appears between 40 and 70 degrees from the surface normal. A three-dimensional mask corner naturally presents oblique local facets to the incoming ions, so the top edge receives the largest effective contact volume and erodes the fastest. A bevel develops, the corner retreats, and the edge rounds, which relaxes the critical dimension and can grow line edge roughness. The same angular physics drives spacing effects and can seed microtrenching where reflected ions and resputtered atoms concentrate near the base. In short, sputter etching is physical and directional. Low mask selectivity comes from mass-driven momentum transfer at energies far above bonding scales. Top corner rounding comes from the increase in contact volume at oblique angles, which is strongest at the corner. Use sputter removal when you need clean directionality, and pair it with lower bias or mild chemistry when pattern fidelity and mask survival are critical. This slide explains chemical etching, where reactive neutrals and radicals meet the surface, form a gas, and that gas leaves the wafer. Because these species arrive without a preferred direction, removal happens sideways and downward at almost the same rate, so the shape is isotropic. Plasma helps by breaking feed gases into highly reactive fragments at low temperature. For silicon, the key fragment is fluorine, and the reaction makes a gas called silicon tetrafluoride that the pump removes easily. This also explains why an oxide mask survives while silicon is etched. On crystalline silicon, the reactions with fluorine or chlorine release energy. The free energy change is negative, so the reaction runs on its own and the product is volatile. On silicon dioxide, the silicon-oxygen bonds stabilize the solid. The same reactions require energy. The free energy change is positive, so the oxide barely reacts under those conditions and protects the pattern. Two gates still control the rate, temperature, and volatility. If the product gas does not have enough vapor pressure at the recipe temperature, it sticks on the surface and a purely chemical path stalls. Now connect this idea to the rightmost figure that compares wet and dry etching. In wet etching, the liquid reaches every exposed surface at once, so the reaction moves in all directions and the result is isotropic. There is one well-known exception. In single crystal silicon, the etch rate depends on the crystal plane because the surface atom density changes by orientation, so certain chemistries make facets and behave anisotropically, which we call crystallographic etching. In dry etching, the same logic applies to purely chemical steps. When neutrals and radicals dominate the reaction, profiles are isotropic because there is no preferred direction. But when ions are involved, the electric field above the wafer drives them straight down. They break bonds at the bottom and speed up the reaction there, and the profile becomes anisotropic with preserved sidewalls. That is the takeaway for this slide. Chemical etching by neutrals is isotropic and its selectivity follows thermodynamics, while directionality appears only when ion energy guides where the reaction happens. This slide explains ion-enhanced etching, the mode where a chemical reaction is helped by ion energy so we get directionality without giving up too much selectivity. Think of it as two ingredients working together. Reactive neutrals or radicals supply the chemistry that can form a volatile product and leave the wafer. Incoming ions deliver energy straight down. They break surface bonds, create reactive sites, and speed up the same chemistry at the bottom of the feature. When the incident ions themselves are reactive, they can also participate in product formation while they activate the surface. The center plot shows the classic synergy experiment by Coburn and Winters in 1979. With xenon difluoride gas alone, silicon etches very slowly, under about 1 nanometer per minute. Add a beam of argon ions near 450 electron volts and the rate jumps by about an order of magnitude. Turn off the gas and leave only the ion beam, the rate falls back again to a slow physical sputter. Faster together than either one alone, that is the signature of ion-enhanced etching and the basis of what we call reactive ion etching, RIE. Now connect that to profile control on the right. Sidewalls are shadowed by the masks so they see mostly neutrals and only weak ion flux, which means mainly chemical etching there. The trench bottom sees the full ion beam, bonds are broken and reactions are activated, so removal is fastest in the vertical direction. The result is an anisotropic profile that preserves the printed width much better than a purely chemical step. A few practical notes help when tuning recipes. There is a threshold in ion energy. Once you reach the range where bonds are broken efficiently, the enhancement becomes strong. Because ions are involved, selectivity to photoresist is lower than in a pure chemical step, and sidewalls can still etch slightly from neutrals, so profiles are directional but not perfectly vertical without additional sidewall protection. In short, ion-enhanced etching sits between chemical etching and sputtering, combining their strengths, high etch rate with better selectivity than sputter alone and the directionality needed for pattern transfer. This slide explains the fourth plasma etching mechanism, often called protective ion-enhanced etching, where we add a passivation step so the sidewall is protected while ions keep the bottom reactive. Here is the sequence. Reactive neutrals create a low volatility film on every exposed surface. This is the inhibitor or passivation layer. Sidewalls receive little ion flux, so the inhibitor stays and blocks lateral chemical attack. The trench bottom is hit by ions coming straight down, so the inhibitor is sputtered away and the fresh surface reacts quickly, which drives fast vertical removal. The result is an anisotropic, near vertical profile even when the base chemistry by itself would etch isotropically. That is why we use this mode whenever the chemistry is too reactive and tends to undercut. Passivation suppresses the sidewall reaction while ions localize the etch to the bottom. Connect this to the aluminum example on the right. With chlorine gas alone, aluminum etches rapidly by pure chemistry and the shape is isotropic. Adding ion bombardment does not help much in that chemistry and can even reduce the net rate because ions knock off adsorbed chlorine before it reacts. Switch the feed to a chlorocarbon such as carbon tetrachloride and carbon-rich fragments form a non-volatile passivation film. Now ions clear that film at the bottom but not on the sidewalls, so the etch becomes directional and a vertical cut appears. If aluminum contains a little copper, non-volatile copper chlorides can further strengthen the sidewall barrier in chlorine-based recipes. To make the idea stick, let us look at one more example, this time with silicon, using the same protective ion-enhanced etching mechanism. The sequence does not change. Reactive neutrals first lay down a thin inhibitor on every exposed surface. This film is a fluorocarbon polymer made from fragments in the feed. Sidewalls receive little ion flux, so the inhibitor remains and blocks lateral chemical attack. The bottom sees the full ion flux, the inhibitor is knocked off, fresh bonds are exposed, and the chemistry runs fast there, which drives vertical removal. For silicon, the typical feeds are fluorocarbons such as C2F6, C4F8, and CHF3. They generate CF2-like fragments that build the protective polymer while fluorine-bearing species provide the etch chemistry that turns silicon into a volatile product. A small oxygen addition is tuned to balance polymer and etch, too little polymer gives rounding and the profile drifts isotropic, too much oxygen overpassivates the surface and slows the cut, and oxygen also attacks photoresist quickly, which is why strong passivation recipes often use a hard mask. Now read the three right side pictures from left to right. Chemical etching only, neutrals reach every surface at once, the opening turns into a smooth bowl, a classic isotropic shape. Protective reactive ion etching in the middle, ions clear the bottom while the fluorocarbon film stays on the walls, the trench cuts straight, width is preserved, and the bottom is clean. Physical etching only on the right, ions sputter slowly with poor selectivity, redeposition and roughness can appear, and without chemistry the sidewalls tend to taper. A few practical notes help when scaling features. If the inhibitor supply is too strong, residue and pinch-off can trap polymer at the bottom after the etch. If the inhibitor is too weak, sidewall attack and bowing appear during long over-etch. Pattern density also matters. Dense arrays consume reactants and can slow the local rate, so dummy fill or gas tuning is used to keep profiles uniform across the layout. So in the silicon case as well, inhibitor on the sidewalls plus ions at the bottom gives a clean directional profile, which is why protective reactive ion etching is the workhorse for trenches, contacts, and other high-fidelity transfers.
Plasma etching removes material by forming a volatile byproduct inside a vacuum reactor. We inject an etchant gas into a chamber where a plasma is sustained, and the exposed solid on the wafer reacts at the surface to create gases that can be pumped away. The left table lists typical etchant gases for common semiconductor materials and the plasma chemistry reactions that produce volatile products. For photoresist, which is a hydrocarbon polymer, oxygen family species convert carbon to carbon monoxide and carbon dioxide, and hydrogen-assisted cracking creates smaller CH fragments, so the resist becomes gas and leaves. For silicon-related materials, the key is to make silicon tetrafluoride, written as SiF4, because it is highly volatile under vacuum. Fluorocarbon feeds such as CF4 or C2F6 supply fluorine atoms that react at the surface. So silicon in SiO2 or Si3N4 forms SiF4 and desorbs. In nitride, the nitrogen part is captured as ammonia, written as NH3, which is also volatile. Because the reactor operates under low pressure, even byproducts with moderate boiling points at atmospheric pressure will sublimate or boil away quickly, therefore removal is efficient. When the plasma is on, many plasma species appear. There are neutral feed molecules, dissociated radicals, positive ions, and electrons. The etch characteristics depend on the density of these species and the energy they carry. The feed gas itself has the highest concentration, but it is far less reactive on the wafer than radicals that come from dissociation. Radicals drive the chemistry that forms the volatile products. Ions accelerated through the sheath strike the surface nearly normal to the wafer and add directionality and synergy. Ion bombardment deserves a clear note. 1 electron volt corresponds to a thermal equivalent of about 7,700 Kelvin, however the actual wafer surface temperature rise from a single impact is minimal. Instead, bombardment activates the surface, breaks weak bonds, cleans inhibitors, and lowers the effective activation barrier, so the chemical reaction rate increases right where we want it. This is the classic physical and chemical synergy in plasma etching. Now read the right side: plasma species, density, and energy. The upper chart represents a capacitive coupled plasma, commonly called CCP. Its plasma density is relatively low, sheath voltage is higher, ion energy at the wafer is higher, and the total flux of ions and radicals is smaller. Dissociation is limited, so only a portion of the feed breaks into radicals, and a large amount of etch byproducts can be observed. The lower chart represents an inductively coupled or electron-cyclotron resonance discharge, commonly called ICP or ECR. Here the ionization and dissociation rates are high, so the radical density is high and the ion density is also high. The sheath voltage is lower for the same power, so ions arrive with lower energy but in much greater number. With many radicals and many ions together, the etch rate becomes high while maintaining strong directionality from the sheath. This slide explains how particle populations in an ionized gas set the behavior of plasma etching. As shown in left figure, a quasi-neutral plasma is sustained by energetic electrons. Near the wafer, a sheath forms and drops most of the potential. This drop holds back electrons and accelerates positive ions toward the surface. As a result, each species plays a distinct role. First, consider the feed molecules that we inject into the reactor. These are etchant molecule gases such as Cl2, F2, HF, CF4, and SiF4. They can react at several hundred degrees, but within the normal plasma etch temperature range their direct reaction with the substrate is weak. There are limited cases where a surface pathway activates the molecule, yet in most processes the molecule is not the primary driver. Next, consider radicals. Stable molecules are dissociated by the plasma and produce radicals with high chemical reactivity. Molecular radicals include CF3, CF2, and OH. Atomic radicals include FO and H. Radicals react readily with the substrate at typical plasma etch temperatures and often live longer than ions in the discharge. Now consider reactive ions. A reactive ion forms when a molecule, a radical, or an atom becomes ionized. Reactive ions can be positive or negative, and the polarity determines both motion and role at the surface. Positive ions originate mainly from electropositive gases that lose an electron. A sheath forms above the wafer and holds most of the potential drop. The sheath accelerates positive ions toward the substrate so they arrive with significant energy and near normal incidence. Representative cations are Cl+, Cl2+, CF3+, H+, and SiF4+. These ions remove inhibitors, open fresh sites, and assist bond breaking, which locally activates the surface reaction. Negative ions originate mainly from electronegative gases that gain an electron. Negative ions are not accelerated across the sheath toward the wafer, so their direct contribution to material removal is small. They influence the plasma potential and they influence the self-bias voltage of the surface. They are also used to mitigate electron shading and differential surface charging by helping charge neutralization during the plasma off period. Representative anions are Cl-, Cl2-, F-, and CCl4-. In the bulk plasma, electrons sustain the discharge by impact excitation, dissociation, and ionization. Radicals are created in that process and then diffused to the wafer with little momentum but with high chemical reactivity. Ions cross the sheath almost normal to the surface and deliver directionality together with local activation. Ions clear weak bonds and open fresh sites. Radicals occupy those sites and form a volatile product. Pumping removes the product and exposes a new layer. Repeating this cycle gives us anisotropy even at deep aspect ratio. Now read the right picture, which follows a fluorocarbon feed through the plasma. Start from molecules such as CF4 and C4F8 at the top. Electron impact breaks bonds and produces a family of fragments. We obtain radicals like CF3, CF2, CF, and atomic F. We also obtain cations such as CF+ and CF2+, and anions such as F- and large negative fluorocarbon ions. The legend groups them as feed gases, cations, anions, and radicals. This network matters because each branch controls a different surface pathway. F atoms react with silicon to form SiF4, which is volatile under vacuum. CFX radicals can link together at the surface and build a thin fluorocarbon film that passivates sidewalls. Ion bombardment preferentially removes that film at the trench bottom where the sheath drives ions vertically. The bottom continues to etch, the sidewall remains protected, and the profile stays vertical. In this slide, I'll explain how electrons create radicals and ions in a plasma, and why energy matters. The left plot shows how reaction probability changes with electron energy, and the right cartoons show the collision outcomes. Although low-pressure plasmas are not in global equilibrium, the electron population is often described by a Maxwellian-like electron energy distribution function. The effective electron temperature for etching plasmas is commonly around 2 to 3 electron volts. Because electrons are about 1,000 times lighter than ions and neutrals, elastic collisions transfer very little energy to heavy particles. What matters are inelastic collisions, where electron energy is converted into internal energy of the target. There are three main inelastic channels: excitation, dissociation, and ionization. Excitation raises the internal state, but keeps the species identity. Dissociation breaks a molecular bond, and creates two neutral fragments that are chemically active. Ionization removes an electron, and creates a positive ion together with a secondary electron. Focus first on dissociation and radical generation. If the electron energy exceeds the weakest bond energy, the molecule splits. For example, an electron hitting CF4 can produce CF3 and F, and the fragments are radicals with unsatisfied bonds. These radicals often live long enough to reach the surface, and they drive most of the surface chemistry in etching. In the plot, dissociation peaks at lower electron energy than ionization. Now consider ionization and ion generation. If the electron energy exceeds the ionization potential, the collision produces a positive ion and one more free electron. For example, an electron colliding with CF4 can yield CF4+, and a second electron. This channel sustains a large electron density, and it supplies positive ions that the sheath accelerates toward the wafer. In the plot, the ionization probability rises at higher energy, so only the high energy tail of the distribution contributes. The electron energy distribution function governs both channels at the same time. At an effective temperature near 3 eV, many electrons can dissociate feed molecules, while a smaller fraction in the high energy tail can ionize them. Radicals from dissociation provide chemical reactivity, and positive ions from ionization provide directionality and local activation. Together, they explain why plasma etching can be both chemically strong and highly anisotropic. This slide explains excitation in plasmas, and how optical emission spectroscopy supports endpoint detection in etching. Dissociation and ionization drive chemistry, while excitation mainly enables process monitoring. During excitation, a neutral species is promoted to a higher energy level, above its fundamental level. When the excited species returns to a lower level, it emits a photon, and the photon energy equals the energy difference between the two levels. The emitted light carries a spectral fingerprint, and it lets us analyze the plasma both qualitatively and quantitatively. Every atom and every molecule has characteristic emission wavelengths, so the apparent plasma color changes as different materials dominate the emission. An optical sensor can detect the spectral change, and it can indicate the endpoint of a plasma etch recipe in real time. The table on the left is illustrative, not exhaustive, and it maps materials, etchant gases, emitting species, and their wavelengths. The variety of light arises from inelastic electron collisions with neutral species. Those collisions also generate electrons, ions, molecules, radicals, and photons, which together form the population of the discharge. Neutral species originate from injected feed gases, from etch products, and from materials released by the chamber walls. The right figure shows a typical optical emission endpoint detection setup used in plasma etching. Light emitted from the plasma passes through a collection lens or an optical fiber, and is sent into a monochromator. The monochromator disperses the light by wavelength, usually in the range from 200 to 900 nanometers. The separated spectrum is then detected by a photomultiplier tube or a CCD sensor, and the signal is amplified for monitoring. By tracking the rise and fall of selected lines for the etchant, the substrate, and the etch product, optical emission spectroscopy produces a clear endpoint signal. For example, when fluorine reacts with silicon, etch byproducts such as SiF2 and SiF4 are generated. These species can be further dissociated or ionized in the plasma, and their characteristic emission lines appear in the spectrum. The graph at the right bottom illustrates this behavior. At the start of etching, signals rise as reactions begin. When the film is cleared, the product signal drops sharply, while the etchant and substrate signals change accordingly. This transition provides a reliable marker for process endpoint control. This slide shows basic steps in plasma etching, illustrated for chlorine on silicon. We will follow the slide from A to D. Step A covers what happens inside the plasma source region. Electrons collide inelastically with chlorine molecules, and two channels dominate. For radical formation, an electron plus Cl2 gives 2 Cl and 1 electron. For ion formation, an electron plus Cl2 gives Cl2 plus and 2 electrons, and an electron plus Cl gives Cl plus and 2 electrons. These reactions populate the discharge with Cl radicals and positive ions, while the electron density is sustained by the extra electrons produced in ionization. Step B brings the species to the wafer and prepares the surface. Chlorine radicals diffuse to the silicon, then adsorb and chemisorb, so the silicon surface becomes bonded to many chlorine atoms. At the same time, the sheath electric field accelerates positive ions toward the wafer, which sets the incidence to be nearly normal. The combination of adsorption by radicals and acceleration of ions establishes the conditions for reactive ion etching at the bottom of the feature. Step C is the reactive ion etching reaction itself. On a chlorinated silicon surface, the chemical path forms volatile silicon chlorides, which we denote as SiClX. There is also an ion-assisted path, where ion impact breaks surface bonds, exposes fresh sites, and increases the rate of forming SiClX. The ions remove passivation at the bottom more than at the sidewall, so penetration through the product layer proceeds downward and the etch remains anisotropic. Step D completes the cycle with desorption and pumping. Adsorbed SiClX leaves the surface as gas phase SiClX, for example SiCl4, and the products are pumped away. Repeated removal exposes new silicon and the sequence continues, while some chlorine can mix into the near-surface silicon lattice and slightly modify the surface. Any step from A to D can become rate-limiting depending on plasma conditions, gas composition, and the substrate. For chlorine on silicon, the balance between purely chemical formation and ion-assisted formation is especially sensitive to the electron density, the bias power, and the surface concentration of carriers.